everyone. I'm Dr. Romeo C. de la Cruz, also from the University of the Philippines, Philippine General Hospital. I am both an optometrist and ophthalmologist. That's why I was assigned to you to lecture about optics and refraction. There are several scope of optics. The physical optics, which pertains to the physical properties of light. Geometric optics is more of the focusing of light as produces retinal images. Physiologic optics is more of retinal process, which produces visual energy and stimuli. And neurooptics is more on the conduction of visual energy to the brain. The main focus of optics and refraction is geometric optics. So there are basic principles of geometric optics. And these are the following: refraction of light rays, prism, divergence of light, spherical lenses, cylindrical lenses, and spherocylindrical lenses. We will discuss this individually. So let's talk about refraction of light rays. Refraction is governed by Snell's law, which states that as light travels from one medium to the other, especially from medium of lower index of refraction to a medium with higher index of refraction, there is bending of light rays. And as it travels, there is a slowing of the movement of the light rays as it travels from lower index to higher index of refraction. And the bending is towards the normal or central ray, which is the dotted line in the illustration. So there are different refractive indices of common ophthalmic material. What I would like you to focus here in the index of refraction of air, cornea, and crystalline lens. The air has an index of refraction of 1.00, while the cornea has 1.37. So there is a big difference of 0.37 in the index of refraction. Cornea being or having a greater index of refraction as compared to air. That is why when light enters the eye, the greatest refraction or bending of light rays happen in the cornea. And as it traverses the crystalline lens, between the cornea and crystalline lens has greater index of refraction. So the light rays again bends when it passes the crystalline lens, and so it can bring a retinal focus. So what is our vision when we are in water or in air? So in this example, what is your vision underwater? So this swimmer, what can he do to see fishes under the water? Okay, and on looking down, he saw a shark. Okay, is there a refraction? Is he looking at the real location of the shark? So should he grasp the shark below or above his line of sight? Is there really a refraction if he and the shark are both underwater? Well, he should swim away as fast as he can. So in this illustration, because they are both in the same index of refraction, there is no refraction happening. Okay? So while if this swimmer's head is above the water, okay? So and he plans to spear the shark, he should analyze it very well. Should he direct the spear above or below the shark? Because in this case, with his head above the water and the shark is under the water, there is a difference in the index of refraction between the air and water. Because the air has an index of refraction of 1.0, while the water has an index of refraction of 1.33. So therefore, there is a refraction happening. Okay? So should he direct the spear above or below the shark? So where is now the actual location of the shark? That is the actual location of the shark after refraction. But actually, when your head or with the swimmer's head above the water, he sees the shark behind the real shark. And that is the image of the shark. So should he direct the spear above or below the shark? So he should direct the spear into the real image of the shark, which is the one nearest to him. Okay, so there are several factors for light refraction. One is the difference in index of refraction, and the other one is the curvature of optical medium. And with the physical laws of refraction, it says that with low index to high index, the light rays is actually bent towards the vertical. And vice versa, when high index to low index, the light rays is bent away from vertical. Okay, so as you see, also there is a greater refraction happening when a light passes from air as it enters to the retina and the crystalline lens. So let's talk about prism. What is prism? Okay, prism is a wedge of refracting material with non-parallel faces and a triangular cross-section with an apex and a base. In prism, light is refracted towards the base while the image is deviated towards the apex. So this is the illustration. So in Prentice rule, it says that for every one prism diopter, there is a 1 centimeter displacement at a distance of 1 meter. So if your object is located 1 meter away, for every prism diopter, there is a 1 centimeter displacement. So let's talk about lenses. Convex lens is a lens that is used to correct hyperopia. It magnifies images. And these lenses actually are um, composed of base-to-base prism, while a concave lens, which is used to correct myopia, is composed of prism that is positioned apex to apex. So what is the prismatic effect of lens decentration? The center of the lens should coincide with the center of the pupil. So we have to determine when we are giving a lens or prescribing a lens to a patient, we have to determine the pupillary distance so that if we make a lens or order a lens, a prescription lens for a patient, the center of the lens, or we call it optical center, should coincide with the pupillary distance. So like in this case, for example, we have a 4 diopter lens in a patient, okay, and if we measure the pupillary distance, it is 60 millimeter pupillary distance. However, for some reason, we prescribe a 64 millimeter optical center. So there's a difference of 4 millimeter decentration. So applying the Prentice rule, we have here 4 millimeter, convert to cm, that is 0.4, multiplied by the amount of your lens, which is 4 diopter. So therefore, we have a deviation of 1.6 prism diopter base out. All right. So this is the reason why we as eye doctors, we don't really recommend over-the-counter reading glasses, because these over-the-counter reading glasses, yes, patients can see with it. They are magnifiers. They can correct presbyopia. However, since these disposable lenses, since the optical centers of these disposable lenses were not made to coincide or to align with the pupillary distance, therefore, while wearing it, patients will definitely experience what we call prismatic deviation or prism effect. Next is the divergence of light. Divergence is the relationship between two light rays striking the eye or emanating from the eye. A negative vergence is light is diverging from a point, while a positive vergence, a light is converging to a point. A zero vergence means light rays are parallel. So this is the illustration for your convergent and divergent. Diopter is the unit that quantifies divergence. It is the reciprocal of the distance in meters from the point where the light rays would intersect if extended in either direction. So the basic lens formula is U plus D is equals V, which U is for versions of light entering the system, while D is the amount of versions contributed by the lens, and V is the versions of light exiting from the system. Okay, so this is the vergence formula. So vergence in diopter is inversely proportional to distance in meter. So if you are trying to get the vergence, the formula is D is equals to 1 over the distance. Okay. So for example, you have a distance, you have a 1 meter distance with the formula of this equal to 1 over distance. A 1 meter will actually give you a vergence of 1 diopter, while a half meter will give you a vergence of 2 diopter. If it is convergent, it's plus, and a 1/4 meter will actually give you a plus a 4 diopter vergence. If it's convergent, it is in plus form. And the opposite is if it's divergent, it is in minus. So like 1/2 or 1/4 meter divergent light will give you a minus 4 diopter, and 1/2 meter divergent light will give you a minus 2 diopter, and 1 meter distance divergent light will give you a dioptric power of minus 1. Okay, so the vergence formula is this equal to 1 over the distance in meter. Okay, these are just an example of what we have just discussed. So using the basic lens formula or the vergence to locate an image, here's a sample problem. An object located 2 meters to the left of a plus 2 diopter lens, where is the location of the image? So we try to identify the location of the image. So one 1/2 diopter is equivalent to 0.5 diopter. So since it is negative vergence because the light rays are diverging from the object. So the object is on your left, which is 2 meters away, or 2 meters to the left of your lens. So the lens adds 2 diopter of positive vergence. This is a convergent lens, as in the sample problem. The dioptric power of the lens is plus 2. All right, so thus the vergence exiting the lens is minus 0.5 diopter. You add with plus 2, that will now become plus 1.5 diopter. That is algebraic addition. So light leaving the lens, or light emanating from the lens with a convergence of plus 1.5, will come to a point by using the vergence formula, will now come to a point 0.67 meter from the lens. So that's how you locate the image in a given lens. Okay, so let's talk about spherical lenses. Spherical lenses focuses beam of light to a point. It could either be a convex or a concave lens. It adds plus or minus vergence to light. So let's talk about principal focus and focal length of spherical lenses. So the image on the left is a convex lens, while the image on the right is a concave lens. So the focal length is measured to the right of a convex lens, while the focal length of a concave lens is virtual, which is measured on the left of a concave lens. So the primary focal point of a lens is a point along the optical axis at which an object must be placed for parallel rays to emerge from the lens and form an image at infinity. Okay, the secondary focal point is the point along the optical axis where parallel incident rays are brought to a focus, as you see in the illustration. So what is the focal length of a lens? Focal length is the distance from the ideal thin lens to its focal point and is measured always in meter. Remember that. So the focal length is equal to the reciprocal of the dioptric power of the lens. So you memorize this formula by heart. This equals to 1 over f, f being the focal length in meter. Or if you want to find the dioptric, or the if the dioptric power is given, you want to locate the focal length. The formula is f is equal to 1 over d. So for example, you have a 4 diopter lens. So f is equal to 1 over 4. That will give you 0.25 meter or 25 centimeter. And a lens with a focal length 10 centimeter had a power of 10 diopter. So next is cylindrical lenses. What are cylindrical lenses? Cylindrical lenses focuses light to a line and not to a point. It has power only in one meridian. A spherical lenses has a power in all areas in all meridian, while a cylindrical lens has a power only on one side or one meridian. It comes with a convex or plus or concave or minus cylinders. And use the use of these cylindrical lenses is to correct the astigmatism. Okay, this is an illustration of a cylindrical lens. That is a cylinder. The horizontal line is the power of the cylinder, while the vertical line is the axis of the cylinder. All right. So two equal cylinders or triangles actually produces a spherical lens. That's why with spherical lens, the power is equal in all meridians. Okay, so spherocylindrical lenses. What are spherocylindrical lenses? So let's talk about optics of spherical and cylindrical lenses. So a spherical lenses form a point image, while a cylindrical lens actually forms a line image. Okay, so a spherocylindrical lenses is also known as a compound lens. When you say a compound lens, it is a combination of both a sphere and a cylinder. So an example is a prescription of a myopic astigmatism, which has a 1 diopter spherical component and a -2 diopter cylindrical component. So this is a compound lens used to correct myopic astigmatism. It has two principal meridians of power acting 90 degrees to each other. And its optics is being called as a conoid of Sturm. In this case, or in this kind of lens, light focused as two focal lines. Okay, so these are the types of astigmatism. When you say simple hyperopic astigmatism, there is zero spherical component and the astigmatism is in the hyperopia side. So the prescription will give you a plano combined with plus 250 diopter cylinder at axis 180. And simple myopic astigmatism, there is no spherical component or no correction for a sphere, but there is a minus cylindrical correction or minus astigmatism. While a mixed astigmatism is there is a concave spherical component or a minus spherical component and a plus cylindrical component. And with compound, when you say compound, the spherical component and the cylindrical component is either both minus or both plus. That is a compound astigmatism. Now, what is a conoid of Sturm? Okay, in astigmatism, we have two focal lines. Again, a spherical lens will give you a point focus or point image, while a cylindrical lens will actually produce line image. So since cylindrical lens has different powers in different meridians, for example, the vertical and horizontal, it also produces different focal lines. So like in this illustration, the vertical portion of this lens produces a vertical line that is the first focal line, while the horizontal portion or horizontal meridian of this lens gives or produces a horizontal focal line. All right, so that's the second focal line. So between the first and the second focal line is what we call the conoid of Sturm. Okay, and in between the conoid of Sturm or interval of Sturm is the area with circle of least confusion. Okay, so let's talk about astigmatic lens correction. Astigmatic lens correction has a power meridian and axis meridian. The power meridian is the curved part of the cylindrical lens. It is the area where it contains correcting power of the lens. Like in the illustration, the horizontal meridian is the curved part of this cylinder. So therefore, if this is a lens, the correcting power of the lens is located at the horizontal meridian because that is the curved part. While the vertical meridian, the 90th, is a straight surface, so there is no power located in that area, which means this is the zero power area, which is being called as the axis meridian. So remember, in astigmatic lens correction, the power meridian is the correcting part of the lens, or it contains the power of the lens, while the axis meridian is the flat part or the zero part, the area where there is no power in the cylindrical lens. Okay, for example, your cylinder is positioned horizontally, like in this case, in the illustration on the right, on the left is -4 diopter cylinder, axis 180. The axis 180 actually is the horizontal line, which means there is no curve in that area. So the power there is zero. That is the flat part of the cylinder. That is the axis. So 90 degrees away is the curved part, which is the power meridian located at axis 90. All right. So if your prescription lens or cylindrical lens is -4 diopter cylinder, axis 90, the axis is the vertical meridian. Being axis, it is the flat part. It has zero power, so it is the axis. While the horizontal line or the horizontal meridian is the curved part of the cylinder, so therefore that is the power meridian. So if you say -4 diopter cylinder, axis 90, the -4 is actually located in the horizontal meridian. So this is the power cross or cross diagram in spherocylindrical lenses. So for example, by the way, it represents the power of the lens acting in every meridian. So in the first example, you have a -3 diopter sphere combined with -250 diopter cylinder axis 180. The -3 being in the spherical component is located in all parts or in all meridians. So -3 is both in the vertical meridians and the horizontal meridian. While -250 diopter cylinder at axis 180, so 90 degrees away from 180 is 90th, axis 90, that is the location of your -250 diopter cylinder. Okay. So the effective power in the vertical meridian is the combination of the spherical and your cylindrical. And since they are both minus, adding them algebraically will give you a total power of -5.50 diopter. While in the horizontal, the -3 diopter remains. Okay. What if the axis is 90 in the second example? So again, -3 diopter sphere is located in all meridians because it is the spherical component of the spherocylindrical lens. So You put minus 3 in the vertical meridian, you put minus 3 in the horizontal meridian. And minus 250 diopter cylinder, the axis is 90. So there is no power in the vertical meridian, meaning to say the minus 250 diopter cylinder being axis 90, the power minus 250 is located in the horizontal meridian. So adding them algebraically, the total effective power of the horizontal meridian is minus 5.50 diopter, while in the vertical meridian is minus 3 diopters. You have to take note of the axis notation of the eye. When you're looking at the patient's eye, the zero notation starts from the left going to the right. So for example, in this left eye, the zero, the axis notation, in the axis notation, the zero is on the left, the 90th in the vertical middle portion, while the 180th is in the nasal portion of the left eye. So on the right, it goes the same. So zero on the left, that is the medial portion of the right eye, and 180 in the temporal portion of the right eye. So that is the axis notation of the eye. So this is important because this is where the area where we need to correct the areas of astigmatism. So let's talk about Jacksonian cross cylinder, or JCC, Jackson cross cylinder. So Jackson cross cylinder actually is a is a very unique lens because it's the only lens that has uh, both plus and minus power in a single lens. That's the uniqueness of Jackson cross cylinder. Okay, so uh, talking more of spherocylindrical lenses, there is such a thing as transposition of spherocylindrical cylinder lenses. So what do I mean by transposition of a spherocylinder lens? Prescription that you see in other parts of in other countries of the world, like in US, if you look at the prescription glasses, you will see them in a plus cylinder form. While most of the countries in Asia and also here in the Philippines, prescription glasses actually is in a minus cylinder form. So whether plus or a minus cylinder form, they serve the same function. They correct the same errors of refraction. However, you just have to transpose or do transposition of spiral cylinder lens. So how do you do that? So in this example, a minus 3 diopter sphere with a combination of plus 2 diopter cylinder axis 180, a plus cylinder form is not applicable in our country. So you have to transpose that to a minus cylinder form. So how do you do that? These are the steps. One, add algebraically the sphere and the cylinder powers. Okay, that will now become, in the example, minus 3 and plus 2 will give you a minus 1 diopter sphere. Second step, change the sign of the cylinder from plus to a minus. And then the third step is shift or rotate the axis 90 degrees away. If your given axis is 180 with plus cylinder form, that will now become 90 with minus cylinder form. So after transposition, your cylinder now will become minus 2 diopter. So just the same, if a prescription done from the Philippines and will be brought in the United States, you will transpose it from minus to plus cylinder. So in transposition, you just change the position or the location of the cylinder correction. However, the effective power of the lens is still the same. Okay. Another point of concern is what we call spherical equivalent in spherocylinder lenses. So what do I mean by this? A spherical equivalent actually is removing or uh, uh, taking away the cylindrical component in the spherocylindrical lens. but you don't totally remove the cylindrical component. You just have to divide the cylinder power into two, get the half of your cylinder prescription. For example, in the example below, plus 2 diopter cylinder, you divide that into 2, that will become plus 1. So you add algebraically the half of your cylinder to the spherical component, and then drop the remaining half of the cylinder. So for example, you have a minus 3 diopter sphere, and then get half of the cylindrical component, which is plus 1, add algebraically, so your spherical equivalent is minus 2 diopter sphere. And this we commonly use spherical equivalent in prescribing contact lenses if you want to drop the astigmatic correction or the cylindrical component. Okay, so let's talk about image construction in optics. So a plus lens, rays passing through the optical axis is undeviated, while rays passing from object point through the center of the lens is still undeviated, while rays traveling parallel to optical axis after refraction by lens passes through the secondary focal point. Okay, and rays from the object which passes through the primary focal point, the first focal point in the illustration, will travel parallel to the optical axis after refraction by the lens. So with plus lenses, after doing all the ray tracing or image construction, a plus lens will actually give you an image that is real, inverted, and a magnified image. So in contrast with a minus lens, rays passing through the optical axis is undeviated with minus lens. Rays passing from object point through the center of the lens is undeviated. And rays traveling parallel to optical axis after refraction by lens passes through secondary nodal point. And rays from the object which passes through the primary focal point will travel parallel to the optical axis after refraction by the lens. So with after image construction and ray tracing with your minus lens, the image that is produced is virtual, erect, and minified. Okay, so that's all about geometric optics. Thank you for listening.